All right. Well, now that we know the history of where we've come from, let's go ahead and get started with where we're going and start our presentations for the day in our new search technology is what we've chosen two themes for this year's symposium. That's also new to this year of kind of structuring our talks to a theme. And so the one we're going to start off with this morning is technology and how that's kind of affecting search planning. And so the first talk of the day, we have planning and evidence search using a probability mosaic. And this is by two members of the Washington State Search Planning Unit, a team we're very proud of in Washington State. So we have Guy Mansfield. He has been active in search and rescue since 2008. He's a member of Everett Mountain Rescue and a director of the Washington State SAR Planning Unit. He has planned and managed large-scale searches in Washington State and has supported searches in all 3 national parks in Washington. He's been recognized at city, county, and state levels for his contributions to SAR missions. In addition to supporting traditional SAR missions, Guy and his team have been working on ways to apply search theory concepts to planning searches for human remains and criminal evidence. And we also have Eric Rosenberg. Eric has been an active leader in search and rescue since 1999. He's currently an operations leader for King County Explorer SAR and is also a director in the Washington State SAR Planning Unit. Eric has served as ops or plans chief for hundreds of missions throughout Washington State and has worked closely with detectives on criminal evidence searches. Eric has a background in geography, is a SAR topo mapping expert, and shares his expertise by being an instructor for SAR topo training classes. So without further ado, Guy and Eric.
Excellent. Thank you very much. Thank you for that introduction. Good morning, everybody. Thanks for the introduction. And I'd also like to acknowledge a couple of our colleagues who couldn't attend in person today, who have been helping out with some of our work here. Peter Templin. Peter is also a member of the Washington State Search and Rescue Planning Unit, and he's been instrumental in applying the planning methodologies that we've been coming up with to actual missions. So we're all in cahoots here for those things. We would also like to thank Kathleen Decker for her very important law enforcement perspective on the work that we've been doing in evidence searches and her input, and based on her experiences in years as a major crimes detective. So I want to acknowledge them and thank them very much. All right. In our work as in the State SAR Planning Unit, we've been called a number of times to assist with evidence search planning, and where we're going to look for human remains or items related to a crime. And kind of over the course of those searches, we've gained experience and we've been evolving ways to use search theory and terrain analysis to kind of help us prioritize where to go look, and hopefully increase the odds of success. So what we'd like to do is share with you kind of how we, the approach that we have, where we started and then the approach that we have now. So, and then we'd like for you to, towards the end, share with us any, feedback and questions and ideas and suggestions you may have in kind of where we're at now. So you'll see that, you'll see a kind of a progression of how we've done a few things and then where we are today and how those have been applied. So, all right. So I'll begin briefly by just reviewing some of the characteristics and challenges in planning for evidence searches. Then I'll follow by sharing some of our early and not always so elegant attempts to formalize probability modeling and when planning for evidence searches. Then I'm going to hand it over to Guy Mansfield, who's going to talk to you about where we are today and show you how we've applied that to some recent searches. Just a few minutes, brief review on a few things that make evidence searches challenging and contribute to low success rates, right? We know some of the main factors are there's, initial actions for concealment. There's, animals can scatter remains. There's passage of time. There's environmental changes. These elements can make it very difficult to, contribute to making things harder to find. And on evidence searches, right, we can be looking for, we could be looking for whole deceased subjects. We could be looking for, other human remains or other items related to crimes, right? When it comes to human remains, we could look for large targets, concealment, clandestine or what was it going to say? Not clandestine, burial sites, sorry, burial sites. We were looking for large items like burial sites, human remains, those sort of things. And for crimes, crime-related objects, we're looking for weapons and clothing, other items related, shell casings, binding materials, things used in concealment. So a lot of these kind of items, a lot of things to go look for, right? So, and of course, we do evidence searches, in just about everywhere. Urban settings, rural settings, wilderness settings, those sort of things. So it kind of runs the gambit. So some of the reasons for low success rates when it comes to evidence searches, especially for cold cases, right, is that that these things, as many of us have probably experienced, can be really hard, right? This image here is from a 10-year-old cold case where we're looking for remains that had been scattered and they've been out there for more than 10 years. There's been a lot of the duff from the wilderness, from the trees. We're covering things up. The items we're looking for are taking on the colors of the dirt. They look like the sticks, and it's and you can see that we've got sifting tables set up there for this one won't here. Where's my laser pointer? So we have sifting tables here to look for smaller items, that sort of thing. So it's not surprising that under these kind of circumstances, right, that it's difficult to find items. That it's not always successful when we're searching for these things. It's going to be pretty challenging. Okay, so when we're planning for criminal evidence searches in particular, it's important to consider some key factors, right, to determine where the location of our targets could be, right? Right. First, you can see that items are acted upon, moved originally by humans, and then they may be secondarily distributed by animals, right? So during plannings, you'll want to systematically analyze and consider these factors in your environment and how those factors interact with your terrain, right? You want to model that sort of thing so that you can come up with these kind of high probability zones. Where within our terrain do these factors, would these factors lead us to say these areas are higher probability zones, right? One of the significant advantages of evidence search planning, especially for cold cases, is we often have tons of time to plan for them, tons of time to over-plan for them, right? So, so now what I'm gonna do is I'm gonna walk you through some of our earlier experiences with evidence search planning and use that, and you'll see there's some examples of how we used all that lead time to begin to wrestle with applying search theory concepts into these types of incidents, right? And then you'll see some, admittedly very rough edges as we started in our early approaches. But I want to illustrate that, our thinking got better as as we look back at each search, and we try to then modify how can we get better at applying some of these concepts. So far and away, our first search here, far and away one of the biggest evidence searches or searches in recent history was in 2018. It was related to a girl named Lindsay Baum. She was an abduction homicide case. She disappeared while walking home in a small town of McCleary, Washington. Hunters had located 9 years later. Hunters located her remains. That was in 2018. Located at least some of her remains in a further away in eastern Washington, quite some distance away, in a forested area. So we got called in to kind of help with this planning. And a quick note is that we do have law enforcement permission to share some of the overall, like how we participate in this, but of course the details and the exact location are not going to be shared. So locations you see are modeled elsewhere. So when we got called in for this one, again, this 2018, kind of our first attempt for a large evidence search of this type, we really looked at, we began by considering, the literature that was available, and could see that, they documented some common characteristics. Things like, primary one is criminals fear discovery, so they take a lot of actions in those spaces. Most criminals will look for a quick and easy way to dispose of a body and evidence. And then, in our Pacific Northwest, especially, where we operate, there's a lot of easy access to locations that afford for forest roads that afford, quick and easy areas to quickly get rid of evidence and do it in a way that's concealed so that the criminals are not observed. So we have a pretty target-rich space for these things. So what we did is, we began by doing our probability modeling by looking at the historical patterns that we just discussed there. We took some of the patterns that documented Bob Kessler's endangered and vulnerable adults and children reference. We did some probability modeling based on distance found from the initial planning point from the initial evidence. We looked at we looked at historical distance off the roads, so about 150 yards off either side of a road. We modeled those, then we modeled the downhill side of the road. So these are matching up with some of the criminal behaviors, and then applying that into our area, right? And then what we did was we mapped each of the points where the models might overlap, right? The distance and distance off the road, distance from the item found, downhill side, where those kind of models overlapped, we then made those planning regions. All right, and so you can kind of see how the density, the color code here, density. And then now again, this is not the actual location. This is just us doing the same kind of modeling in a different location. So then what we then did is we took a little step further, is we then assigned a subjective values to each of those mapped probability zones. So we said, if distance from the item found, so areas closer to the items found, we get higher scores. Further away gets lower scores. You get 30 points for being within 150 yards of road, 30 points on the downhill side, that sort of thing. So we did that kind of scoring, and you can see it here, and then we thermal coded those priorities so that red would be the higher priority area, so areas with the most kind of points. So this was kind of our initial attempt to bring these models together, make these planning regions, and then we divide these up into search sections once inside those, right? So that was our initial kind of rough stuff. And again, we use this as a subjective POA modeling, right? We subjectively gave some scoring, and we applied those to give us a subjective POA to begin with. All right. And then during our searches, I think there were like 6 operational periods. We captured GPS tracks, and we were able to plot these over our probability mosaic that we're calling these here, the thermal coded ones. We then used, for a variety of reasons, we never ended up being able to calculate the coverage, right, for a variety of reasons. But what we did is we went in and we came up with this idea of doing visual estimation of coverage. So you basically just look at the tracks and the coverage you have in each section, and you kind of say like, yep, like in this area, we have pretty good coverage, and then maybe get an estimate of how much that coverage is, and from independent raters. And then we visually see that there's some areas of higher probability that may not have as much coverage, and we kind of use that for our guidance for coverage. So while we felt that our probability modeling provided a useful guide, we also admittedly said that the subjective POA is squishy, to use a technical term, and so we weren't entirely happy with that initial effort, but at least we felt like we were doing something in a progressive way. The next big evidence search came along in 2020, and it's actually very similar circumstances. It was evidence had been found for a similar 10-year-old case of a child in a similar kind of environment, and an initial item was found by civilians, mushroom hunters in this case. And so by this time, we're a little bit more tuned into the concepts of search theory, as you'll see. So we began our planning along that path, kind of along a little bit better understanding of what we're doing with the search theory. And of course, we started along that path, and then we may have taken a methodological detour or two. You'll see here in a second. All right, so we started planning with some on-site visits. Law enforcement And some of us, we went out to actually walk the terrain where the item was found, and then started visually looking at these things and thinking about these applied the different factors for kernel behavior and animal scatter and whatnot, and areas of opportunity for quick concealment, right? And so part of that, we kind of came up as we're walking through there. We kind of came up with this concept of something we call event lines, right? In grim terms, these were mapped representations of high probability locations where the victim might have been murdered, right? We ended up using these concepts in our probability modeling. So again, we're walking out there, thinking about these things, and we're kind of identifying high probability zones based on all the factors when it comes to planning for evidence searches. Right, now we're starting to map it up. We're starting to model it to the terrain that we're seeing. All right. So then we went to the more traditional search theory application, and we made planning regions that were roughly based on terrain features, right? Then we mapped our objects, where the item was found, and the event lines, drainages, and streams and trails where animal paths in that area. So we mapped all those things, and then we prioritized the planning regions by using a probability, an assigned probability using a consensus, proportional consensus model. So we had initial POA score for each planning region. Okay, and then we then mapped the search segments within each planning region. So we cut up we provided the search segments, and we try to do sort of regular polygons, but really what we're attempting to do here is optimize for canine searching. So smaller, 0.3 acres, 0.5, 0.3 to 0.5 acres for HRD, for really detailed HRD work. Right. And this is kind of what came out. So right here we're following along the search theory kind of the typical search theory concepts. And then here's where we took a little bit of a turn. So we know that our search segments would inherit the probability density, the PDEN of our search segments would inherit from the PDEN from the region. And then we said, like, well, that's nice, but again, we wanted to be able to highlight these high probability zones, right? This is what we're struggling with. Is like we want to be able to indicate where the high probability zones are within this map and bump those up in priority, right? And so what we did is we did another kind of subjective PDEN incrementation this time. So based on some of these factors, proximity to the IPP, proximity to the event lines, trails, paths, drainages, those sort of things. And so we took the initial PDEN that we're getting from the regions, and then we bumped those up subjectively based on the criteria that we wanted to show for the high probability zones, right? And so then we thermally coded as you can see here, thermally coded the results. And then for the search effort, right, we captured the GPS tracks from both our canine and our search dogs, and we derived search coverage in two ways. One is we did the calculations of track line length and effective sweep width, or estimated effective sweep width. And then we also did another round of the visual estimation of coverage. We had 3 independent raters just visually look at the tracks that were in a segment and estimate how much coverage that segment got, because we had the time, and and we were a little bit skeptical. Like, so we wanted to compare how calculating the coverage versus visually estimating the coverage of each segment. And so we're a little bit skeptical about our visual assessment coverage, and we ended up calculating the correlation coefficient and between the two scores, and we were pleased to see they're actually, the R value was actually quite high, right? And maybe that's a subject for another paper or another symposium. But anyway, that was some of our efforts that we've been going on there. So these two search events that we did a couple of planning. So our first one, this is kind of a summary of that one, right? And the summary, both these incidents we began with to factor in known patterns for criminal behavior and animal behavior. We experimented with some different approaches to mapping the planning regions and the segments. right? One we did some subjective POA, another one we did subjective PDEN incrementation, right? Again, to try and get to those high probability zones and get those to show as possible higher priority areas to go look. So while we felt that we were attempting to systematically apply search theory concepts, we weren't really comfortable with sorts of ideas that we had implemented, right? So so with that, I'm going to hand off to Dr. Guy Mansfield, and he's going to explain to you kind of where the next stage that we've evolved to. So Guy, over to you.
How's that? On? Yeah, we go. Volume up a little bit. Okay. I'm just going to take 30 minutes here to familiarize myself with the equipment, and then we should be in good shape. All right, laser pointer. Okay. So Eric has been describing some of our past, I'll say, history of experimentation with mixing together some search theory methods with terrain analysis and some other methods. And as he said, we were pretty much okay with some of the work we've done and a little bit less than okay with some other of our efforts. So what I'm going to do now is to bring you up to date in terms of where we are with our evidence search planning approach. And again, the purpose of this is to solicit feedback and wisdom, or you can throw tomatoes at the end from this group. I want to begin this section by cautioning audiences that this part of the presentation is rated FOI for few original ideas. Okay, you'll see we're trying to be systematic, but you'll recognize many of the concepts we're going to be mixing together here. So as Eric alluded, we want to begin, or an early step, is to consider at a qualitative level typical criminal behavior of H. sapiens, okay? And so we can make pretty high-level qualitative statements when thinking about what's the probability of finding concealed bodies or evidence. And we know from previous research that's been compiled in Bob's book and other sources that likely places to look are within, let's say, 100 yards of roads, particularly on the downhill sides of roads. Our detective colleagues say a great place to look is where people have dumped stuff over the road before. Other areas of higher probability would be where there's vegetation cover or any sort of concealment. And then, as Eric mentioned, we're also very much interested in the potential impact of animal scavenging on human remains. So in order to look into this, we took a detour into forensic taphonomy, okay? You want to impress friends tonight over drinks, you could say, oh yeah, I just came from a talk in which we discussed forensic taphonomy. And that means anything that happens to a body between the time it gets out in the woods and the time that search and rescue comes upon it. So in our research, we found that a researcher named Haglund had begun to put together some systematic thinking about locating human remains. And he began with a series of pretty high-level questions. Are the remains scattered? Is there evidence of that? Do you have an IPP? From where was the body scattered? In Haglund's research and in others, actually, you can drill down to an extreme level of detail in terms of asking the question, well, in this particular environment, what are the possible scavengers that might have been out there, you know, ranging from bears to bugs? And then based on the season and the ecology of the area, what are the likely scavenger candidates, and drilling down into their behavioral patterns. We don't, in our planning, we don't drill down that far, but there's a rabbit hole you can go down there. One thing we were most interested in was the question, are there likely trajectories of dispersion of bones, for example? And the reason for this is a very common situation for us is that one bone will be found in the woods somewhere, and law enforcement will come to us and say, okay, we want you guys to go out and see if you can find more. So along those lines, I started to do some research and thought, well, it'd be really great if there was actually patterns of distribution, if those bones that you found could point to more bones to find. And I started out with pretty high hopes, but was a little bit disappointed, as we'll see. So there is a limited amount of research based on a very small sample size, and I'll just show you a couple of examples here. So Beck reported in a study out in the Sonoran Desert environment that there might have been maybe sort of an elliptical or linear pattern of distribution. Again, I think the N was like 2, 3, or 4 different cases here, okay? In I think a review paper, Gleason also showed some data which, you know, you could possibly interpret as being maybe a linear pattern, but my conclusion was we didn't have enough data to make a conclusion, okay? So another really important question to us was, okay, we found a single bone, how widely do we need to search to be satisfied by our effort? And, you know, I'd be a really happy camper as a search planner if there were data that said, well, if there are coyotes involved, the bones will always be scattered with a 100-meter radius, okay? Sadly, that's not the case. There's one study I ran into by Mannheim. She reported an average distance of like 24 meters, which to me seems very short distance. This was in a Louisiana environment. I don't know all the details. She did report a maximum distance of 200 meters. And on sort of the other extreme, if you look at Hagelin's paper, he reported that coyotes could move remains up to 3 kilometers, which is very discouraging from the point of a search planner. So again, no firm guidelines there, or if they're guidelines at all, they're sort of very rough. Here's a picture from an actual case. A number of years back, we assisted law enforcement. And this is a case where there were like 3 bad guys, and 2 of them did the 3rd one in, and law enforcement believed what had happened, or found out what had happened, is they loaded the 3rd bad guy into a trunk, went driving off into forest roads, and at some point it was believed they stopped and rolled their friend over the side of the road, okay? So we had an interesting start to this. If you look in the upper left, we were actually able to get cell forensics data, and from that plot sort of average speed at segments over this road, with the theory that the slower segments, is indicated by the red and the orange here, were areas where it was more likely maybe that this average speed was slow because they stopped, okay? We don't know that for sure. But interestingly enough, in one of the orange segments, an alert ground searcher was walking along the road and saw something right over the side. And sure enough, that became our IPP. The next day, we brought in a large number of HRD dogs. And how many folks run HRD dogs? We got one, just one in the audience. Well, and you know that typically in their careers, HRD dogs may not have a large number of finds. These HRD teams were just having a field day here. And turns out there were remains scattered all over this area, the downhill side of the road, close to a pullout, close to where people had dumped stuff over the side before. So if you look at this, the greatest distance is out here beyond 500 meters. Maybe this is a linear pattern, maybe. And this just, I don't think that's a linear pattern there. Again, conclusions for this is we only have rough guidelines in terms of distance. All right. But based on the research we did, we were able to compile a small number of what I think of as qualitative probability statements. So if you're thinking about the impact of animal scavenging, there's probably an increase with proximity to your primary site. Also increased probability along streams, drainages, trails, fence lines. For example, for coyotes, they'll move along fence lines. And if you can find them, certainly it might be higher near animal dens or nests. So at this point now, for each incident, what we do is we identify a set of qualitative statements about criminal behavior and qualitative statements about animal behavior, okay? We will also mix that in with input from detectives in terms of specific terrain features. For example, if we're searching a property, maybe there's a burn pile, maybe there's a swamp, we will add that in. And what we do is compile a list of what we call evidence probability factors, or EPFs, because everything has to have an acronym. So an example, here's our qualitative statement, probability increased along roads. In this case, we actually have data that's summarized in Bob's reference. And so we add a evidence probability factor that says our search grid contains areas within 100 yards of a road or a path. Similarly, for animal behavior, we add a factor that says our search grid contains areas within 200 yards of a drainage, okay? Now, just a note here, for the 100 yards within a road, we actually have data. For the 200 yards within a drainage, we just picked a number. We're now at the point where we have a composite list of evidence probability factors. Again, these are incident specific. And we want to obtain relative values for each one of these. So we use a proportional consensus methodology. Okay, we get input from detectives, investigators, informed planners. We go through the proportional consensus process and compile the input and end up with a relative value for each one of these scores. And you'll notice that this proportional consensus process is very much analogous to using a proportional consensus to derive a planning region POA. So not too much new there. We throw their scores into what we have a proportional consensus calculator, and we simply add up for each factor, which is a column here. So factor A might be proximity to a road, but we simply add up the scores from each of the consensus participants. No rocket science here. We simply sum that to get a big number or a small number. Okay. All right, so at this point now, we have a list of our probability factors. We have relative scores assigned, and we take, as a next step, we take each of those probability factors and represent those on the map, all right? So in this example, we can see these red buffers are a 100-yard buffer within roads and trails. The yellow shapes here, which may be a little bit harder to see, are areas where there was denser tree coverage or foliage, more concealment, okay? Oh, another thing I'll point out that we do when we can is, since this was a historical case, we were actually able to go into Google Earth, time travel back in time, and the image that you see here on the screen shows us what the foliage cover was like back in closer to the actual time of the incident. We then overlay a uniform grid. And when we started out doing this, we would like draw this by hand in Syrotopo, which is perfectly feasible, but only mildly painful. Operationally, we use segments that are 50-meter squares. This makes it easier to draw. And also it turns out to be like 6/10 of an acre, which is a reasonable size for close searching and HRD assignments. So in this example, you can see that the search grids or the segment grids in this area are going to contain multiple underlying probability shapes. We then use a spreadsheet to compile these. Again, we do this by hand. An advanced step would be to have this done in a GIS system. And just as an example, for grid segment E09, it gets points for being near the IPP, it gets points for being near a road, and it gets points for containing an area where there's brush coverage. And we add up those points, and in this spreadsheet, we simply ordered them by points. And then the next important step is that we take those scores, normalize them on a scale of 0 to 100, and that yields a distribution of probability of area across our grid. We use those POA calculations, the numerical numbers in later calculations of coverage and POD. But really for us, the easiest thing to do, especially when we're showing them to law enforcement, is to represent those thermally coded, like here. And you can see that around these areas here, there's a cluster of higher probability areas as indicated by the red and then orange shading. All right, so at this point, we've done what I think of as sort of the front end of the search theory cycle. We've gathered as much information as we can about the incident. We've considered behavioral factors of both the bad guys and the animals. Where important, we also consider terrain factors and historical factors. And we ended up, we start then with an initial statement or initial distribution of probability of area across our grids. What happens next then is we go out and actually search those segments. We can calculate coverage and POD, again, by making an estimate of sweep width, which is a whole other talk. And anybody who wants to stay tomorrow can come, and we won't talk about that tomorrow. Then we can compute and show the residual POAs. So diagrammatically, it looks like this next slide. Here's on the left is our initial POA probability map. The middle slide here, maybe a little bit hard to see, but densely packed GPS tracks modeled for searching the heck out of these areas with our ground teams and canines. And then you can see after we compute the residual POA that these areas have cooled down substantially. So just as a quick aside for fans of Syrotopo fans, raise your hand. Hey, okay. One of the cool things that we learned from MarinSAR was that you can actually take the different layers and set them up as map sheets and then have them all queued up and ready to go. So I'll just give you a 5-second demo of that. So here we have 6 or 7 map sheets. They're all queued up and ready to go as map sheets in Syrotopo. And just by going down and selecting these and fading them in, we can see first, here's the original search area. Here's the search area when we went back in time. Here's the search area with the grid overlaid, bringing in another map sheet. Now we have our probability models, another map sheet. Now we have our initial thermal, another map sheet, initial thermal with a plain background, another map sheet showing the search tracks, another map sheet showing their residual thermals. So this is really neat trick in Syrotopo. Also very useful if you have a complex multi-operational period search. You can show the results and tracks and assignments from multiple operational periods and store them and display them in these map sheets. All right. With an introduction helped by Calvin and Hobbes, I'm now going to wind up my presentation with just 2 examples of where we've been using this methodology. And for those who may not be able to read the captions in the back of the room, Calvin starts out, he goes, "Oh, I can't believe it, we got to plan another evidence search. How are we going to find anything out there in the woods?" And they want to plan with search priorities. And he turns to Hobbes and he goes, "How's it coming?" And Hobbes says, "Not so good, I'm out of crayons." And using crayons for coloring is an apt description of our early efforts at Sartopo. So, all right. But first, I'm pleased to announce the results of a randomized controlled trial that we just did, where we took 1,000 evidence. Oh, wait, we didn't actually do this. We didn't actually take 1,000 evidence searches and randomly assign them to old methods and new methods, and then run the Mansfield's non-parametric test for hopeful trends in random data. So we can't provide the results of that comparison to you. All right, maybe perhaps in a future Syrotuck meeting. All right. So I can describe a little bit about one sort of hot, cold case that we're working on. This is a continued search for evidence in a wooded environment. We've compiled our list of evidence profile factors. This is based on input from major crimes detectives. We're working with the Attorney General's Homicide Task Force. We're getting input from investigative analysts and a geographic profiler, and all of that is informing our list of evidence profile factors. We're now at the point where we can actually use a GIS fishnet tool to create our nice grid. And incidentally, this again is not a real search area. This is a fake one I picked. We're still doing manual scoring of the search segments, but because we have search tracks in this area before, we're now at the point where we can use our GIS system to calculate the POD from previous searching in each search segment. So we're making advances in terms of computational stuff. All right. The last project I can describe in a little bit more detail. All right. And this is what I think of as our Fort Simcoe project. Fort Simcoe is the site of a Native American boarding school, I think in the late 1800s. And many of you are aware of the history of the Native American boarding schools, where children were removed from their families and kept under pretty cruel conditions. And there's evidence that on this property, as well as other Native American boarding schools, that there may be unmarked burials. And it's become important for the tribes to see if they can verify that and find out more information. And so we're working with the Yakima tribal representatives to see if we can search the Fort Simcoe site. And the way I describe this at a high level is nicely encapsulated with a quote from J.R. Frost. See, for any search to be successful, 2 things must be true. First, searchers must be looking in the right place. And second, searchers must be capable of detecting the search object. So we address the first challenge by using our probability modeling, and we address the second challenge looking for very old buried remains by using specially trained HRD canines. Okay, so now I'm going to detour a little bit into the canine world here. So why use HRD dogs? Well-trained, highly certified HRD dogs are extremely sensitive biosensors. Importantly, they're non-invasive sensors, okay? There's a lot of cultural sensitivity, as you can imagine, about just going in and digging up a whole bunch of stuff on the old sites. But with the dogs, we can get pretty good indications that there may be something there that could be followed up with ground penetrating radar or other technologies. So just checking my notes here. Yes. I'll use this highly technical slide here to describe the science of HRD detection. What they detect is what are called volatile organic compounds, or VOCs. I'm not an expert on this, but there's a sort of a side branch of HRD dogs, historically trained or historical HRD dogs that in their training are trained to detect extremely low odor thresholds, like going out to Civil War cemeteries. And these are the types of dogs we're using for the Fort Simcoe project. And they've been shown to be able to locate human remains hundreds of years old, or possibly more. All right. So in planning for the Fort Simcoe site, we did another cool thing in Sartopo here. We were able to get a sort of a historical map and overlay that against the real-time aerial. This gives us an idea of where the structures were, the children's dormitories at the time. There we go, good. That's the hint that I may be running out of time. I'm getting close. I'm getting. And also we collected the information for this incident was fairly sparse. We did terrain analysis. We had some historical data, and also from our tribal representatives, we got sort of general information about areas where burials might have occurred. So we put that all together, historical information, terrain analysis, and came up with our curated list of probability factors. Then we went through a consensus process to assign a relative value to those. In our probability factors, we were also able to get some relatively high resolution LiDAR data. So we were able to add as a probability factor, does the search grid contain a LiDAR anomaly? And you can see there's a couple of anomalies here we were interested in. And so we ended up with a thermally coded probability mosaic. Use that to say, well, okay, our search dogs can only work for like less than a half a day at a time. If the weather's good, let's search the high priority areas first, which would be our red areas and our orange areas. In results to date, we are getting canine indications in the high probability and medium high probability areas indicated by the little yellow dog markers there. And again, I've blurred all the background for confidentiality reasons here. So a summary of our results is shown in this next slide. And you can see that in our high and medium high probability areas, we are getting, that's where we're getting the trained final responses, okay? Now at this point, anybody with any background in research design is starting to feel uncomfortable because what you've noticed is we haven't searched any low probability areas, all right? So we don't know if in fact we'd see the same percentage of canine responses in the low probabilities areas as well. In other words, we don't have enough data to do the chi-square test that we ought to be running here. We do plan to do some searching in the low probability areas, and that will be an interesting result, which maybe we'll report at the next meeting. So as of now, we know that our sensors are performing pretty well, but we don't know that our planning methodology is performing well. Okay, but we're being systematic about it. All right. All right. So just to wrap things up, I want to point out that our use of a uniform probability grid is not an original idea. Okay, this slide is earlier work from Bob Kester, where he took 6 different lost person behavior models and then, excuse me, built up and represented a thermally coded mosaic. Really nice looking picture. Lastly, a comparison, or almost lastly, a comparison between our approach and sort of the traditional maritime search approach. In both of those approaches, in the last two columns here, we derive a probability of area and probability density, and among other things, display those as a probability mosaic with a uniform grid. Coast Guard uses agent-based modeling, incorporating the last known point and factors such as wind and current. Whereas in our model, we use the evidence probability factor approach and run that through a consensus process to derive relative values. Okay. Last slide before break, coffee and donuts. Okay. At least I think that's what's on the agenda. All right. So in summary, what we do is to collect as much information as we can, couple that with on-scene scouting, incident-specific information. We consider criminal behavior at the qualitative level, animal scavenging behavior, and then, again, tailored for each specific incident and working with investigators and law enforcement, we come up with an incident-specific list of evidence profile factors. We use a proportional consensus process to assign a relative value to each one of those. We map each evidence profile factor on our map and overlay a uniform grid. And then with a manual scoring process, which could be eventually automated, I think, each grid, we distribute probability of area across the grid. And that can be represented here, as we've seen, as a thermal mosaic. All right, with that, I'll stop and see if we have any questions or if anybody wants to throw those tomatoes that got distributed earlier. We've got a number of questions. We'll start back here. Oh, whoops.
Hey, Guy, how's it going? Hey, so how do you qualitatively assess criminal activity? What's a quality criminal?
Quality control. Yes. So again, if you go back to the slides here, let's see if this is what you're asking. Everybody's getting dizzy now. Okay. There's actually a pretty good body of research that's been documented in Bob Kester's pamphlet, and there are other references, such as the detection of human remains by Edward Killam, if you can believe that. Okay. And there's a lot of both anecdotal and data-based information about how criminals behave. And that's a pretty good source. I mean, it's much more objective than us, the way we think about, or the way we process the animal behavior. It's a little bit more squishy on that end. But for example, you can go into the Endangered and Vulnerable Adults and Children manual that Bob has published, and he's got a page of statistics in terms of percentage of cases and distance off the road. That's very useful.
Guy, this is your fault. You put up the spreadsheet. Are you doing any shifting POA calculations based on the data you're collecting? Doing any shifting POA calculations as you move through the search segments and adjusting your resource accordingly for that?
Yeah. So the short answer is no. What we tend to do is just, as I've done here, just display the residual POA. And we look at that and say, okay, the POA, the residual POA is high here and low here. You could do that if you wanted to, but we tend not to do that.
Quick question on the RD process. What are you typically using to establish your average range of detection
yeah.
as a target?
Yeah. So usually we're in a situation where we're looking for really old remains, possibly buried. So we just, and I've read some of the research, but we usually just pick, I'm trying to remember what, like 12 inches or something. Just a really narrow sweep width. And on the assumption, and for both canines and ground searchers, on the assumption that we're being either conservative or pessimistic, or however you describe it, and that when we use that, our results are going to be relative, across the calculations. So we're not going for the absolute truth in terms of, what the real sweep width would be. We're going for a relatively pessimistic estimate. That's probably an area that could be explored more. And I know there are some studies out there, and I think Ken Chia has some recently published papers on canine research. And so we might fine tune that a little bit more based on research, but like I said, we just tend to be really pessimistic. Yeah. And again, because when you get into the canine world, and I got to be careful here because some of my friends are canine people. When you ask them about sweep width and conditions, they'll go, oh, it's different every day and it's different every hour and this could be happening and you can never tell. And all I want as a planner is a cosmic average number. And it's hard to get that out of the canine people. But anyway.
Right now, what are the depths that the canines are detecting at?
Oh, good question. The question is right now, at what depth can canines detect remains? And I wish my canine expert were here. I don't know the answer to that. Yeah. If you come to the National Missing Persons Conference on Thursday, there's a person who knows the answer to that question, but.
We have a question from Charles Twardy. He says, nice presentation and thorough detailed work. Great to see the evolution of automated tools too, and sketch of a motion model for criminals/animals. He would like to know, did you look at archaeology literature? They have to deal with animal disturbances too. Most don't use search theory, but I have found a few that do.
Okay. No, that's a good suggestion. We have not done any dives into archaeology literature. And so that's something I'll put on my list.
Any other
Okay.
questions? Anything online? Great. Well, that brings us to our first break, and in maybe another Syrotuck first. Regardless of giving Rick LaValla the mic, we're running a little ahead of schedule. Oh, we have one more question, actually.
Actually, two more popped in online. Lori Hall would like to know, who's your canine expert? And Ken, you said his name, last name, or Chichia. He says, my take is pessimistic is better than conservative. When you underestimate POD, you're lingering in the initial high POA areas and risking not expanding the search effort when you need to. By the way, our last paper had fairly extensive numbers for human visual search as well as dogs.
All right. So the answer to the first question is my my canine partner for the Fort Simcoe search is Suzanne Ilschult. And Suzanne and I will be talking on Thursday in the big conference. And the second, thank you, Ken, for that. I've looked through at least some of your papers and we'll need to go back and study those a little bit more. So.
Great, perfect. Well, thank you, Guy and Eric. Let's give them another round of applause.